we're looking at numerical computing with NumPy. So you can click the open link here and that will open up the lesson page. And on the lesson, you will be able to watch the video now and later. And you also have the option to watch the same video in Hindi. Now, if you have questions during this lecture, you can ask these questions on the discussion forum. So there is a link to the discussion forum. So this is the discussion forum and you can log into it with the same ID that you used to enroll for the course. And you can just ask questions here. You will see a big blue reply button here on the bottom. So just click the reply button and ask a question. So now I'm going to open up the first notebook. So the topic is numerical computing with NumPy, and this is a notebook you can open up. So here now I'm going to run the notebook. If you're joining us live, you need not run the notebook right now. Please don't, because there are thousands of us, so that may slow things down a little bit for everyone. So I'm just going to run it right now and you can run it later after the lecture. So we click run and then we click run on Binder to take this Jupyter notebook which you're looking at here and then run it online. So when you click the run button, it may take a couple of minutes to start up. This is because this is a free online service and it is provisioning some servers for you. Okay, so while it gets started, let us just go through some of the material. So this course is called Data Analysis with Python, and the data in data analysis typically refers to some numerical data. So things like stock prices, sales figures, sensor measurements, weather data, sports scores, database tables, and things like that. Now the NumPy library provides specialized data structures and functions and other tools for numerical computing in Python, that is working with numerical data. Alright, the Jupyter notebook is now opened up. So this is running on Binder on an online platform. You can also run this on your own computer and there are instructions here to run this on your computer locally. So I'm just going to open up this Jupyter notebook right now. The first thing I always like to do is go kernel and restart and clear output. This is to clear all the outputs from the previous execution so that we can see the outputs fresh. And I'm just going to hide the toolbar here so that you can see it better. As I was saying, NumPy is a library that helps us work with numerical data in Python. So why we might need NumPy? Since Python itself also supports a lot of arithmetic operations and things like that. Let's look at that using an example. So let's say we want to use climate data, so things like temperature, rainfall and humidity in a region to determine if the region is well suited for growing apples. Okay, so a really simple approach for doing this would be to formulate the relationship between the annual yield of apples. So let's say in tons per hectare. So whatever is the annual yield of apples in a region, we relate that to the climatic conditions like the average temperature, which would be probably in degrees Fahrenheit, the average rainfall in millimeters and the average relative humidity, and formulate that as a linear equation. So we could assume that the yield of apples is some weight W1 times the temperature plus some weight W2 times the rainfall plus some weight W3 times the humidity. So we are expressing the yield of apples as a weighted sum of the climatic conditions. Now obviously this is an approximation because the actual relationship may not necessarily be linear because this is a linear equation, but a simple linear model like this often works really well in practice. And then what we might do is we might do some statistical analysis of the historical data. And based on that, we may be able to come up with a reasonable set of values for the weights W1, W2 and W3, right? So just based on looking at some historical data. So here is an example set of values. So now you have these weights W1, 2, 3. Now, given some climate data for a region, we can use these weights to predict what the yield of apples in the region might look like. So here we have the data for 5 regions. And let's say we want to identify what might be the approximate yield of apples in Kanto. So for that, what we can do is we can convert this information into variables. So the temperature, rainfall and humidity, all of these become variables. And then we can substitute these variables into the linear equation, the formula, to predict the yield of apples in that region. So here the yield of apples in Kanto becomes the temperature times W1 plus the rainfall times W2 plus the humidity times W3. And once we do that, we get back the result 56.8. and we can print it out that the expected yield of apples in the Kanto region is 56.8 tons per hectare. Okay. So far, it's a pretty simple calculation that we've done with a bunch of variables, but to make it slightly easier to perform the same computation for multiple regions, what we can do is we can represent the climate data for each region as a list of numbers, or what in mathematics is also called a vector. Because otherwise we might end up creating a lot of variables. For 5 regions, we end up creating 15 variables. For 50 regions, we end up creating 150 variables, and that's just a lot of code to write. So rather, what we are going to do here is we're going to say that the Kanto region is represented by this vector or this list of numbers. The first number represents the temperature, the second represents the rainfall, and the third represents the humidity. Then similarly, we represent all the other regions also using these vectors. And again, temperature, rainfall, humidity are the 3 elements of the vector. For the set of weights that we've used, W1, 2, 3, those can also be represented as a vector together. So now we have the region, each region is a vector, and the set of weights is a vector. So we can now write a function crop yield to calculate the yield of apples or any other crop for that matter, because you just have to change the weights for a different crop. So we can calculate the yield of apples given the climate data and the respective weights. Okay. So here we have a function which takes the which takes the region, it takes a set of weights, and then it performs some calculation and returns the result. So let's observe what it does. So maybe let's just look at the Kanto region and let us look at the weights. So what we want to do is we want to multiply the first element 73 by the weight 0.3. Then we want to multiply 67 by 0.2, and we want to multiply 43 by 0.5. So in some sense, this is an element-wise multiplication. And then we want to add up each of these products. So we get 3 products, so we add them up. So the way we do that is we set a result to 0. And then we use this zip function. So this zip built-in function returns pairs. So you can actually check what zip does. Let's see. So we say for item in zip, Kanto and weights, we simply print the item. So it turns out that it creates pairs out of the 2 lists. So it returns 73 and 0.3, 67 and 0.2, 43 and 0.5. So since these are pairs, or what we call tuples in Python, so these tuples can be converted into variables. So I can pull out the variables x and w. So x would have the value 73 and then w would have the value 0.3. So here you go. And then that's repeated for each element. So now what we can do is we can simply multiply x times w. And that is what we have done here. We have multiplied x times w. So 73 times 0.3, 67.2 and 43 times 0.5. And we have added them into the result. So in effect, it has the exact same effect as what we had done earlier. So temperature multiplied by W1, rainfall multiplied by W2, humidity multiplied by W3, and then we return the result. All right. So that's our crop yield function, and we can verify that we call crop yield with the Kanto region and the same weights, and we get back the same result, 56.8 tons per hectare. And we can do the same thing for the Johto region and for the Unova region. So already we've simplified things a bit by writing this function. Now, the calculation that we've performed, the element-wise multiplication of 2 vectors and then followed by a sum of the results, this is also called the dot product of 2 vectors. And this is just a linear algebra term, and the dot product means exactly what I just said, an element-wise multiplication of 2 vectors followed by a sum of the results. And you can learn more about dot products here on Khan Academy. It's a great resource if you just want to brush up linear algebra in general. But now the NumPy library, which is specialized for doing numerical computing and performing operations on numerical data, provides a built-in function to perform the dot product of 2 vectors, because this is such a common operation. But to do that, the lists that we have, the data that we have, must first be converted into a special data structure called NumPy arrays. And to create NumPy arrays, we first need to import the NumPy module. So I already have the Python library NumPy installed, This was done when we clicked the run button. So there was a set of requirements with the Jupyter notebook. But if you do not have NumPy installed, you can do pip install NumPy minus upgrade and minus minus squared. And this is just to suppress the output, but pip install NumPy should do it. So you can run this to install NumPy, and don't forget the exclamation character. But now we import NumPy as NP, and now the NumPy arrays can be created using the np.array function. Alright. So if you're seeing this part for the first time, so all we're doing here is we're saying that we want to import the NumPy module, but instead of calling it NumPy, we want to call it NP. So that when we want to use the array function from NumPy, instead of writing NumPy.array, we can just write np.array. So this is also called aliasing. Okay. So now we create the Canto region, the data we simply call NumPy.array, and then we just pass in the same list of numbers that we had earlier. So nothing is really changed yet. And you can see here we print it out and we can just see that this is a NumPy array with the same list of numbers. Then we have the weights. So this is once again a NumPy array. It simply contains a list of numbers. But when you check the type, you will see that each of these has the type ND array, right? So this is no longer a Python list. This is now a special data type which is defined and offered by NumPy. Okay. And just lists, the NumPy arrays behave like lists in many ways. And one of the ways is just the indexing notation. So if you just use the indexing notation, you can get back the 0th element, which is 0.3 from weights, or the second element, which is 43 from Canto. But they also differ from Python lists in many important ways, and that is what we are going to see next. Okay. So now remember, we wanted to compute the dot product, which is the element-wise multiplication followed by sum of the results. We can do that using the np.dot function. And a good way to see what the np.dot function does is just say help np.dot, and that's going to tell you what it does. So there's a lot of documentation here, and it gives you a lot of information about it. And then at the bottom, you will see a bunch of examples as well. So you can just see how to use this function. So now we call np.dot with Canto and weights, and we get back the same result, 56.8, except that now we just need to write a single line of code. If we can actually achieve the same result with even lower level operations. So NumPy arrays support arithmetic operators. So here, if we simply do Canto, let's just print out these arrays so that we see it. So remember when we talked about element-wise multiplication? So if we just do Canto star weights and run that, so that actually performs an element-wise multiplication of the two vectors. And then what we can do is we can take that, so that is a NumPy array, and then call dot sum on it. And now this dot sum operator, the dot sum method simply returns the sum of all the elements in a NumPy array. All right. So these are two convenient things that you could not do with Python lists. So these give us a very nice way to write the same expression without having to write a loop, without having to write a function, and so on. Okay. Yeah, and that's what we just looked at, the element-wise multiplication and sum of two arrays. Okay. So before we move ahead, we're already starting to see some benefits of NumPy arrays. So there's one that we've already seen, which is the ease of use. Now, instead of having to define loops and custom functions like crop, you can write very small, concise, and intuitive mathematical expressions like Canto star weights dot sum and get the same results. But another important reason to use NumPy is performance, because NumPy operations and functions are implemented internally using C++, and Python offers a way where you can write something in C++ and expose it, connect it with a Python function. So there's an interface available. So NumPy operations are written in C++, which is compiled down to assembly code. And what that basically means is it is machine code already. So the Python interpreter is not involved in the actual calculation, and that makes the calculation much faster. Sometimes we see, so that makes the calculation much faster. And whenever you want to have a claim like this, that something makes the calculation faster, the best way to do that the best way to verify it is to just check by creating an example. Okay. Here's an example Here we are going to create a million elements, a list containing a million elements. So here we have a list. This is a Python list. And then here we have another Python list. So there are a million elements here, 0 to 1 million minus 1. And then there are a million elements here, 1 million to 2 million minus 1. So two lists with the same size. And then we also convert those lists into NumPy arrays. So now we have two lists and then we have two NumPy arrays with the same number of elements. Now we use this special time command. So this is something special to Jupyter. So you put in 2 percentage symbols and then time. And what this does is this calculates the time it takes to run this cell. Okay. So here we are doing the dot product using a for loop, similar to this, what we did inside crop yield. So we just did a zip and then we got back the values and then we added them to a result. And to do that over 2 vectors of size 1 million, that took about 200 milliseconds. Now let's do the same thing, but this time let us use a NumPy array. So we have the same NumPy arrays and then we run it. Just use np ... and that just takes 2.4 milliseconds. So that's where you can see we get the same result back, but the np ... is 100 times faster than using a for loop. And this is what makes NumPy especially useful when you're working with really large data sets with tens of thousands or even millions of data points. Alright, that's the benefit of NumPy. Now before we go ahead, let us just save our work. So I'm just going to import the Jovian library and run jovian.commit. And this will ask us for an API key. So this is to capture a snapshot of your notebook. So you can go to your Jovian account. So just visit jovian.ml and log in and copy your API key and then paste it back here. Now when you do that, what happens is this notebook gets captured, the entire snapshot, the inputs, the outputs, and that gets saved into your Jovian ML account. So you can view it here. And this binder instance, because it is running online, it's a temporary free service. So this might get shut down, but if you keep running jovian.commit from time to time, you will not lose your work. Okay. So moving right ahead, now we can actually go one step further and represent the entire climate data for all the regions together using a single 2-dimensional NumPy array. So here we can say the climate data is np.array. And here we pass in not a single list of numbers, but a list of lists. So we have a bunch of lists inside the outer list, and each list represents the data for a region. So this is the region data for Kanto, and this is the region data for Johto, and then all the other regions. And then each column here, so each element in the list represents a data point about the weather. So the first element always represents temperature, the second element represents rainfall, and the third humidity. And I've written it in this fashion, but you don't have to. You can write them all on the same line. But it helps to look at it like this, because this is what, if you've taken a linear algebra class in high school, you might recognize that this is what is called a matrix. Or if not, you can just look at it as a table of values. And it has 5 rows, 1 for each data point, and it has 3 columns, 1 for temperature, rainfall, and humidity each. Okay, so we create this array, and then we get back, once again, we get back this array object, but this time this is a 2-dimensional array, right? It is no longer a 1-dimensional array. And that is what makes NumPy arrays so flexible, that they can have any number of dimensions. So here is a 1-dimensional array. This is what we looked at, a vector. And then here is a 2-dimensional array. So here there are 2 rows. So just we have 5 rows here and 3 columns. Here there are 2 rows and 3 columns. And then this is a 3-dimensional array. So here you might have 1, 2, 3 in this direction. And then inside that you might have you might have 3 elements each. And each of those elements itself could be a list, right? So you can have 1D, 2D or 3D arrays in NumPy. And since these arrays, and you can actually have 4D and 5D and any number of dimensions, you just have to keep nesting lists inside lists inside lists. And since NumPy arrays can have any number of dimensions and different lengths along each dimension, what we can do is we can inspect the length along each dimension using the dot shape property of an array. So if we check climate data.shape, you get back the value 5,3. So let's see how we arrive at that value. So the way it works is you first look at the outermost bracket, And then from the outermost bracket, you see how many elements are there in the outermost list. So the outermost list has 1, 2, 3, 4 and 5 elements. And that's why you get 5. Then you go one step in. So you can just pick up the first value. So let's say 73, 67, 43 and see how many elements that has. So that has 3 elements and hence you have 3. Now suppose each of these elements was also a list, then you could count how many elements were there inside each inner list and that would give you the third dimension. So and we see an example of that. So here we have weights. This is a vector or a one-dimensional array. So we can check the shape of weights, and the shape of weights is just the tuple containing 3. So the output of shape is a tuple. The number of elements is the number of dimensions, or also called the number of axes in NumPy, and the length along each direction is the number that is there at that position. So since this is a 1D array, you get back one number, and that number is 3 because it is a vector of size 3. Okay, so then moving forward, the next kind of array is a 3D array, and then you can have 4D and 5D. But for 3D, you can notice here, and this is a little difficult to show because we can only write in 2 dimensions. So you can see here that we have this 2D array or a matrix, and then we have another matrix. So this is, you can think of it as 2 matrices sitting side by side forming a cuboid. So this kind of a structure. And to guess the shape, let's try and guess the shape here. So we look at the outermost bracket and then we say, okay, in the outermost list there are 2 elements. So the first element is 2. Then in every inner list there are 2 elements again. So the second element is also 2. And then inside those elements you have 3 elements, right? So then the third element is 3 for the shape. So hence the shape is 2 by 2 by 3. Okay. So now you might wonder what happens if I do not have the same number of elements. So you can do something like this and then try creating this array and try printing out the shape of this array. Try looking at the array and see if NumPy is actually creating a n-dimensional array or not. Okay, it's a good exercise to just try this out. So one other thing to keep in mind is that for the purpose of efficiency and performance, elements in a NumPy array all should have the same data type. And you can check the data type of an array using the dtype property. So for instance, the weights. So this is an array containing some floating point numbers. If you check dtype of weights, you will get back a dtype float 64. So this is again important that the NumPy data type, NumPy has its own data types different from the Python primitive data types. The reason for that is Python's primitive data types support a wide range of values, but NumPy limits its data types to certain set of values. So for instance, float 64 means that only 64 bits of space in the memory will be used for a floating point number. And similarly, if you check, let's say if you check climate data, this is of type int64. So it can only take 64 bits of data to store an integer. And that's the reason NumPy has its own data types. But in general, there is a 1-to-1 correlation. If you're using floats, you might end up seeing float 64. And if you're using climate data, if you're using integers, then you might end up seeing int 64. Okay. One interesting result from this is that if an array contains even a single floating point number, then all the other elements are also converted to floats. So for instance, the way we define array 3, let me just grab that once again. So here we just defined array 3 where all of these numbers are integers, but the last one is a floating point number. And if you check the dtype, that turns out to be float. And even when you print it out, you will notice that all these numbers have been converted into floats. Okay. So that's just a little bit about when you're dealing with different dimensional arrays, how do you understand what their dimensions are, how many axes there are, what is the length along each axis, and what is the data type contained in it. So coming back to our example though, we have the climate data is represented as, so there are 5 rows, one for each region, and then there is 3 columns for temperature, rainfall, and humidity. So now we can compute the predicted yield of apples in all the regions using a single matrix multiplication. right? And this is where you will need to know a little bit about matrix multiplications. And I've pointed to a resource. Once again, there are 3 or 4 videos that you can watch to understand this. But roughly how it works is this. So this is our matrix containing all the data. So when we multiply that with the vector containing the weights, what happens is we get back a vector as a result, and the vector will have, the first element of the vector will be 73 times W1 plus 67 times W12 plus 43 times W13. So basically the dot product of this row and this weights vector. And similarly, the second element will be the dot product of the second row and the weights vector, and so on. So the matrix, when multiplied with the weights, will give back a vector, and each element of the vector will be the dot product of that specific row with that specific with the weights vector. Okay, and that is what we want. So now and the way to do that in NumPy is to use the mat_mul function. Once again, NumPy gives an inbuilt function for matrix multiplication. So this here, what we're doing is we're taking the climate data and we're taking the weights and we're doing a matrix multiplication. So this first element comes by multiplying, doing a dot product of this with this, and then the second element comes by doing a dot product of this with the whole vector, and the third element comes by doing the dot product of this with the whole vector, and so on. And another way to do the matrix multiplication overall is to simply use the @ character or the @ character. So the @ character represents matrix multiplication in NumPy. So we do the same thing, climate data at weights, and we get back the same results. So now that's pretty convenient. We've taken all our data, all our operations, and then reduced them down to a single line of code for the entire data set. And that is what makes NumPy and libraries in general so powerful, because they offer all of these. Behind this single @ character, there is a lot of complexity that is being hidden from you, and you just have to think of it in terms of a matrix multiplication. All right. So let's take that one step further. Now, so far we've been working with 5 data points. Let's go a little bit further and try and work with a file. So what we'll do is we will download a file, climate.txt, which will contain 10,000 climate data points. So it'll look something like this. Temperature, rainfall, and humidity. So the first row simply describes what information this file contains. And then each row or each line of the file will contain the information for one region. So this is the temperature, rainfall, and humidity in region 1, and for region 2, and for region 3. So in a sense, you can see here that this is like a table or a spreadsheet, but represented using plain text files. And it is separated, the data is separated by commas, and there is one data point or one what is called sample on each row or each line of the file. So this kind of a format is called the comma separated values format. Obviously, because these values are separated using commas. Okay. So we are first going to download the file, and the way to do that is to use the urllib library. So the urllib module in Python offers a lot of utilities for working with URLs, like making requests, downloading files, and specifically we want to use the URL retrieve function, which is present inside a sub-module of urllib. So we need to import urllib.request because that is what contains the URL retrieve function. And then we give it, so we call urllib.request.urlretrieve, and then we give it the URL that needs to be downloaded and the file name or the path where we want it to be downloaded. So we just want to download it in the same directory as the Jupyter Notebook. So I'm just going to give the file name climate.txt. So now the file should be downloaded. And you can check this by going File, Open, and you should be able to see here that you have climate.txt here. If you click on climate.txt, here you will find that this is as I mentioned, this is the header. It describes what each column contains, and these are all the data points. And there are about 10,000, you can verify it. But a better way is to just load it up as a NumPy array. So when a CSV file contains all numbers, it's very easy to load it up as a NumPy array. So the way to do that is using the gen from txt function. So np.gen from txt, And once again, you can use the help function on np.gen from txt to see what it does, or just look it up online on the documentation. But we just need to use 3 of these arguments. It supports many more. So the first argument that we give it is the file name or the full path of the file. In our case, it's just climate.txt in the current folder. Then we need to provide what the delimiter is. So what is the separator between the data? So in our case, the data points are separated by commas, but sometimes these are separated by colons, sometimes these are separated by the tab character. So we just want them to be separated by commas. And finally, we want to skip the header row, right? So because the header row, this is not numbers, this is just some metadata or some information about the data. So we can skip that by providing the number of header rows to skip. So we just do that. And then let's print it out. And there you go. You have the climate data. And because there are so many elements here, NumPy just truncates it by printing dot. But if you check the shape, you will find that there are 10,000 rows and each row contains 3 elements. So temperature, rainfall, and humidity. So we can now use a matrix multiplication operator to predict the yield of apples for the entire data set using a given set of weights. So let's take these weights, 0.3, 0.2, 0.5, the same weights that we had earlier, and let us just multiply it. So we do climate data at weights, that performs a matrix multiplication, and that will, in just one line of code, give us back the entire results. So these are all the yields. So you can see that this is the yield for the first region, this is the yield for the second region, and so on. And that gives us back all, and you can see that there are 10,000 results here. Okay. And then what we might want to do is we might want to take the yields that we have and add that as a new column inside the climate data array. So just as we have temperature, rainfall, humidity, we might want to just add another element here that will represent the yield. And then we can write it back to a file, right? So this is the common flow, that you get some data file, you pull it in, you perform some analysis, you perform some operations, you get some results, and then you take those results, create some output, and write it back to a file. So to do that, now to add the yields back to the climate data as a 4th column, so we are going to use the numpy.concatenate function. Okay, so I'm going to call numpy.concatenate. This is used for joining 2 arrays, and then you need to give it a tuple containing the arrays that you want to join. So we give it the climate data and the yields. Ignore this reshape for a moment. And then you need to give it the axis or the direction along which you want to join them. So for example, what we want to do is we do not want to add more rows to the data, right? We want to add more columns. So if we wanted to add more rows, that means we were adding things into the outermost list. So that would be the 0th dimension or the 0th axis. So by default, the axis will be 0. But we want to add it inside. So to add it inside, we are going to mention that we want to concatenate along the first dimension. And that is why we have set axis equal to 1. So we pass in the climate data and we pass in the yield. And then I will let you figure out why this dot reshape is required. You can try running this line of code without it, and then you can try looking up the documentation for reshape, and I'll let you figure out. And if you're not able to figure it out, you can ask on the forum and then we'll answer it there. Okay. But all said and done, what this does is this concatenates the result. So you can now see that we have a new array called climate results, which contains three columns from the original data, and then the 4th column is from the yields that we have just calculated. Okay. So here is the visual explanation of concatenate. So what we had here, let's say this was the yield, this was the data for the regions, so temperature, rainfall, humidity, and in our example we only had one row of output. So we only had one column of output, so you can ignore these two. So we simply had the yield of apples and the yield of apples here. So when we call concatenate with axis 1, so these get attached along the columns. If you call them with axis 0, they would get attached below. All right. So you can experiment here. So the best way to actually understand what a NumPy function does is to just experiment with it and then read the documentation using the help function. And for most NumPy functions, you will actually find some examples at the bottom of the documentation itself. Okay. So use these cells, these empty cells, to experiment with np.concatenate and np.reshape. Alright, so now let us take the results that we have and let us write them back to a file using np.savetxt. So I think you're getting the idea here that for pretty much everything that you want to do, there is a function in NumPy. And I'll tell you in some time how to find the right function. But here we are just going to take the NumPy function, the savetxt function, give it the climate results, and say we want to write it to climate results.txt. So just these two are enough. But then I have included some other things here just to make it a little bit nicer. So by default, NumPy will write almost 10 decimal points for each number. We don't want that. We can just put in 2 decimal points. So I've just put in this formatting string to just put in 2 decimal points. And then we have this header. So if you want to include a header at the top saying that this represents a temperature, rainfall, humidity, and yield of apples. So that's why we can use the header argument. And finally, there's a comments argument. In this one, I will let you figure out what this comments argument does. So you can simply remove this argument and then try and running it and see what the difference is. Okay. So we run savetxt and that writes the data results back to climate results.txt in this format. Okay. And once again, you can open the file and check that it has the expected output. All right. So as I just mentioned, NumPy provides hundreds of functions for performing these operations on arrays. And here are some common functions. So for mathematics, you will find numpy.sum. So you can not only sum the entire array, but you can also sum just along a particular dimension or along one or more dimensions. Then you have numpy.exponent, numpy.round. So for rounding numbers, for array manipulation, you have concatenate, you have split, you have stack. Then you have matrix multiplications, dot products, transpose, eigenvalues, and you also have some statistical functions like mean, median, standard deviation, and things like that. So how to find the function that you need? You do not need to remember all of these functions, and it can sometimes be hard to find exactly what you need. So the easiest way to find the right function is to do a web search. So just do a search on any search engine, Google, DuckDuckGo, wherever, and try to formulate what you want to do into a single line as clearly as possible. So for example, what I searched was how to join NumPy arrays, and that led me to a tutorial on array concatenation, and that is where I got the code for this operation. So I was not sure what to use, so I just searched how to join 2 NumPys, or you can search for something more specific, how to add a column to a NumPy, and then you will find some result, and that is a good place to start. The next place is probably just to go through the documentation. So there is a full list of array functions. You can, and we'll go through that list a little bit later. So you can just go through the list and just try, and it is categorized based on different criteria, things like this. So you can find the right function there. And finally, you also have the Jovian.ml forum, the course forum. So you can always ask on the course forum, and the course forum is really active. So you will probably get the fastest answer by asking on the forum. Okay. All right. So once again, before we continue, let us just save a snapshot of our work. And in general, when you're working with Jupyter Notebooks, especially on Binder, but also on your local computer, just keep running Jovian.commit from time to time. It's like saving, but it's saving your work to your Jovian account. Okay. Okay. So we've seen arrays and we've seen functions operating on these arrays. But I also want to spend some time talking about arithmetic operations. So NumPy arrays support arithmetic operators like plus, minus, star, and the interesting thing is that you can obviously perform these arithmetic operations. So what we call element-wise operations between 2 arrays. So here we have array 2, array 3, and if I do array 2 plus array 3, so that's going to add up each element and it's going to return an array of the same shape. And now you might wonder, okay, what if these 2 arrays do not have the same shape? Then you can try it. That's something that you can experiment with and find out, right? So when they have the same shape, most of these arithmetic operators perform an element-wise operation. But what you can also do is, instead of adding an array of the same shape, you can just add or do any arithmetic operation with just a single number. So here we have array 2. You can see array 2 has a value 1, 2, 3, 4. And then if we just do plus 3, so 3 gets added to every element of the array. Okay, so you can see 1, 2, 3, 4 becomes 4, 5, 6, 7, as we might expect by adding 3. And then we've seen element-wise subtraction. This works as expected. So you can see that if I subtract from array 3, array 2, each of these differs from the corresponding element by 10, and hence we get back this result. You can divide by a single number. So here's division by a scalar. We've already seen element-wise multiplication. And then you can also do things like remainder, right? So you can take array 2 and you can find the remainder of array 2 with a number like 4. And these are all the remainders. Now, that's great, but NumPy arrays also support something called broadcasting. And what that does is that it allows arithmetic operations between two arrays having a different number of dimensions, right? So they can have a different number of dimensions, but their shapes must be compatible. So let's take an example and let's work through it. Let's understand it using an example. So here we have array 2. It has 3 rows and 2 columns, so it has the shape 3, 2. And then here we have array 4, and this simply has the shape 4. Now what we can do is we can write array 2 plus array 4, and that is a perfectly legal thing to do in NumPy. And what NumPy will do is NumPy will check, and actually it is, you can see it visually here. So here we have an array, right? And then here we have a smaller array. So what NumPy will try to do is it will try to take the array with lower number of dimensions and replicate it a few times. So here the array gets replicated 3 times because it has to match 3. But here this array 4, 5, 6, 7 will get replicated 3 times. So in a sense, what you will end up with is that NumPy will automatically replicate array 4 in this fashion. So the 4, 5, 6, 7 will now become 4, 5, 6, 7 3 times. Okay. And then the addition can be performed, right? Because now the shapes match. So now we can just do array plus array 4, and you can see that has the result. As you might expect, 4, 5, 6, 7 gets added to these, 4, 5, 6, 7 gets added to these, and 4, 5, 6, 7 gets added to these. And you can just verify this completely. Array 2 plus array 4 replicated. Oops, yeah. And you can see that we get the exact same result. All right. So this is the idea here. This is the idea of broadcasting. And here is a visual explanation of the same thing. And then the thing to remember is that broadcasting only works if one of the arrays can be replicated to exactly match the shape of the other array. So for instance, here we have array 5, and we have array 5 dot shape is just 2, and then we have array 2. So now if we try to do array 2 plus array 5, even if you replicate the 7, 8 3 times, let's try that. Let's write it in a replicated fashion. So array 5 replicated. Okay, so this would be 7, 8 and 7, 8 and 7, 8. So even when it's replicated, what happens is that these dimensions, these shapes don't match up, right? So you have the same number of rows because of the replication, but the columns don't match up. And because the columns don't match up, you get a value error that the operands could not be broadcast together with the shapes 3, 4 and 2. Okay. So broadcasting is a very powerful technique, and it's useful because now you do not have to create this replication for one. And in fact, when NumPy does the replication, it is only a conceptual replication. That means it does not actually create copies of the array. So it saves on memory, it saves on, improves the performance. So it's just a way of conceptually replicating or increasing the dimensions of a smaller array for the purpose of an arithmetic operation while still having good performance gains. So just try it with a few examples. Try it with 2-dimensional arrays, try it with 3-dimensional arrays. So maybe take a 3-dimensional array and to it try to add a 1-dimensional array and see what happens. Okay. And in general, this is true with most things, but specifically with NumPy, the more you experiment with these things, the better you understand it. So you can hear somebody, you can listen to somebody explain these things for hours together, but you will not get how it works unless you experiment with it and see how it breaks. And that's very important. Okay. And then apart from arithmetic, NumPy arrays also support comparison operations. So things like double equal to, not equal to, greater than, less than, and so on. So here we have two arrays and we can check if corresponding elements are equal. So you can see here that some of these values are equal. So 2 matched with 2 and 3 matched with 3, and that's why we have true here and then we have false here. So now this is an array of booleans, right? So you can actually check this. So if I do dot d type, that has the type bool, and the same holds true with any comparison operator. Okay. Now, why might you want to do that? One important thing to remember is that even though these are comparison operators, the result itself is not a boolean. It's actually an array of booleans. So that's very important. It's an important thing to keep in mind. And one common use case of something like this could be to count the number of equal elements in two arrays. So what you might do is you have array 1 and array 2, and we want to know, for instance, that if we compare the corresponding elements, the elements at the same positions, how many of these are equal? So 1 and 2 are not equal, 2 and 3 is equal, 3 and 3 are equal, these two are not equal, 5 and 5 are equal. So the way to do that is you could first do array 1 compared with array 2. So that would give you a list of an array of booleans, and then you could call dot sum on it. So now what dot sum will do is it will try to add up the booleans, and remember that true evaluates to 1 and false evaluates to 0 when they are being used as booleans, when they are being used in an arithmetic operation. So that will just give you the number 3, which is the number of matching elements between the two arrays. All right. And then you can imagine now, you can use your imagination to think of other use cases where this might be useful. Okay. So that's about array operations and broadcasting. One thing that we did not go into too much, and we'll get into now, is how to get data out of a NumPy array, right? If you have a multi-dimensional array, and we looked at this briefly where we said that like lists, you can index into NumPy arrays, and that is possible, but then NumPy actually supports a much more powerful indexing notation. So it extends Python's indexing notation to multiple dimensions, and it does so in a fairly intuitive fashion. So what you can do is you can provide a comma separated list of indices or even ranges, and you can use that to select a specific element from the entire array. So let's take this array and you can select a specific element, let's say this one, or you can select specific portions, right? You can even select just what are called slices or sub arrays from the NumPy array. And we'll see a few examples of that. Okay. So here we have array 3. This is a NumPy array and it has the shape, and you can guess the shape here. It has the shape. So if you see the outermost list, that has 1, 2, and 3 elements, 3, comma, and then if you go one step inside, here you see 2 elements, so 3, 2, and then the innermost one has 4 elements, right? So the shape should be 3, 2, 4. And this is a good exercise just to visually look at an array and try to tell the shape and guess what np.shape will return, or the array.shape will return. So now let's say we want to grab a single element out of it. Let's say we want to, and the way to do it is so along each dimension of the shape, you provide which element you want to access. So here we are passing in 1, 1, 2. So let's see. And the way I find it easiest to do is just to work from the outside. So now we have 1. So that gives us, well, from the outermost list, this is 0. So this is 1. So we take this. And in fact, we can just check this as well. So if you just do array 3, 1, you get back just this element, right? And then we have 1 again. So inside this array, we ignore this and then we choose this. So we get back 1 again. So 1, 1 returns this, or you can see it as this. And then finally, we have 2. So here 0, 1, 2. So this should give the result 36, right? So that's how indexing works, and I find it easiest to just work all the way from the outside. And let's take an example of indexing using ranges. So now we are no longer getting a single element, but we are actually getting a range of elements from along each dimension. So here what we are saying, let me just print out array 3 again. So here what we are saying is along the first dimension. That means along the outermost list. In the outermost list, we want to start from the first element. So we want to skip the 0th element, start from the first element. So we skip this entire element altogether. And then we take this, and then we want to go till the end. So we take the first element and then second element and however many elements. So remember list indexing, when you're using ranges, if you leave one side of the range empty, that means you want to go till the end. So this is the same as doing 1:3, but 1: just says 1 and then everything ahead of it. So yeah, so you have this 15, 16. So now you are left with these two. And again, I just find it very easy just to break it down a lot step by step so that there is no confusion. So as I expect, doing 1: here is going to return this. Okay. Then we are saying that in the second dimension, we only want to keep from 0 to 1. So in the second dimension, we want to start at 0. So that means in every inner list, and by inner list this, right? Not the innermost. We're just going from, let's say this is actually dimension number 1. So the outermost was dimension 0, and then this is dimension 1. So let's just use 0 indexing. So outermost was dimension 0, and now we're at dimension 1. So this is dimension 0, and then here we have dimension 1. Now within dimension 1, we want to take the 0th element, which is this, and then we want to skip the first element, right? So the range from 0 to 1 means only 0, because the end point of a range is not part of the range. Okay, so we want to keep the 0th element, but we want to skip the first element. So if I put in 0:1 here and run it, so what I expect to see is that this element should go away. And you can see that element went away, and the same thing happens everywhere along that dimension. And now finally, we have the final dimension, the third dimension, the dimension number 2. So 0th, first and second dimension. So in dimension number 2, we are saying we want to start from the beginning, and that's why it's blank. And then we want to go up to the second index, but not including. So that means we want to take the 0th index and we want to take the first index. So for each of these elements, we just take the 0th element and the first element. So we should end up with 15, 16, 98 and 32. Okay. And one thing to note here is that wherever you are using ranges, the number of dimensions does not reduce. So when we use exact numbers for indexing into an array, each time we use an exact number, the number of dimensions reduces. And then when we use a range, that preserves dimensions, because a range is saying that the result of a range selection is also an array. So along each dimension, we are still keeping an array of some kind. Okay. And then you can mix indices and ranges. So once again, let's take one more example maybe, and then the rest I will leave for you as an exercise. So here we have array 3, and then we are saying that we want to take 1:, so that means we probably want to exclude this element, and then we want to take these, and then we want to take this. And then within these, we want to select 1, 3. So 1 would be this, and then inside that 3 would be 0, 1, 2, 3. So we would be left with 18, but we would also be left with 43. So you can do this step by step again by just putting 1 index and 2 indices and 3 indices. Here you go, we end up with 18, 43. Okay. And then here is another example where we have 2 ranges and then you have 1 index in between. And here you have fewer indices. One thing that you can also do is you can actually leave out, if you want to go all the way from start to end, then you can just put a colon, and that will preserve that entire dimension completely. No selection will happen there. You can also use less than, so if you have 3 dimensions, you can use 1 index, you can use 2 indices, you can use 3 indices, but if you try to use too many indices, you will get an index error. Okay. So this notation and the results that we just got, these can seem confusing at first, especially if it's coming to you in such a short time. But what you should do is you should take your time and experiment so that you become comfortable with it. Okay. And use the cells, create some cells below. So just, by the way, I'm pressing the B character. So escape plus B creates cells. So just create some cells and then try out some experiments. And here is a visual representation. So here you have a NumPy array, and you can create this array over here, and you can try out these examples and see how that works. Okay, it's all about experimenting. The more you experiment, the more you understand it. Okay, and so now we've looked at pretty much everything NumPy has to offer. And one last thing that I want to share is how to create NumPy arrays. And we've seen np.array, that is the easiest way to do it. And we've also seen gen from txt, which can take the data from a CSV file. But you can also create arrays, some special arrays using some direct functions. So you can create an array of all zeros. So np.zeros, and then you give it a tuple containing the shape that you want to create. And that will give you, let's say this is a 3x2 array. So it contains all zeros. This is also called the null matrix or the null array sometimes when you talk about it in mathematics terms. Then you have these np.ones. So all of these are 1 and it has the shape that you pass to it. So the shape can be a tuple or the shape can be a list. It doesn't really matter as long as it is something that can be iterated over. You can create the identity matrix. So this is useful if you're performing some matrix operations where you just want to pass in the identity matrix. You can create a random vector or a random matrix. So for NumPy has a .random module, so np.random, and inside it you have the rand function, and then you also have the rand_n function. So what's the difference? The rand function picks uniformly a value between 0 to 1. But the rand_n function picks it from a Gaussian distribution. And this is where you need to know a little bit about probability and random distributions. But if you don't, you can just use rand_n and be well most of the time. And rand_n generally gives values in the range of -2 to 2. It can even be higher. It can generally be lower than -1 to 1. But because it's picked from a probability distribution, it can have a wide range of values, but a lot of the values will be concentrated around 0. Or specifically, technical terms will say that it has a mean of 0 and a standard deviation of 1. Anyway, but if you don't understand those terms, don't worry about it. But one key thing to notice here is that while these normal array creation methods take tuples as the shapes, for rand and rand_n, you need to pass in the shape as the arguments, right? So there's no tuple here. So this will actually lead to an error. Yeah. So that's just a small quirk in the np.random module that sometimes might cause values. But you can experiment with this and you can check the documentation, just call the help function and you will understand how to use it. Then you can create arrays with a fixed value. So here we are creating a 2x3 matrix containing the number 42. And you can create arrays, you can create a range. So you can say np.arange. So this is the analog for range in Python. So we are saying that we want to start at 10, we want to end at 90, and we want to take steps of 3, right? So np.arange. So you can see 10, 13, 16, 19. It goes up all the way up to 88. And I can check the shape of this. And the shape, it seems like there are 27 elements here. Now, when you have this range, what you can do is you can take this, or when you have any array in, and what you can do is you can actually change the shape of the array. So what you can say here is I can take this result of np.arange, which has 27 elements, and I know that if I reshape it, if I call reshape, and I pass in 3, 3. What it does is this creates a 3D array where it has the length 3 along each dimension. So essentially what it's doing is still the same numbers, 10, 13, 16, 19, 20, 25. It's just inserting brackets at the right places to make it look like a 3D array. And that is why the reshape function can be quite useful sometimes. And remember, you cannot just reshape this array containing 27 elements to any size. If I tried 3x4, that will fail because the number of elements does not match up, right? Here you have 27 and here you have 12. That cannot match up. So it has to be something like 3x3. It can be 3x9. It can be 1, 27. So you can actually increase the number of dimensions while still keeping the same structure, not changing too much, and things like that. One interesting thing is that because the total number of elements is fixed, while reshaping, you can leave out one of the indices, right? So you can just leave out, you can just say 3, 3 minus 1, and NumPy will automatically calculate that in total you need 27 elements. So then this number should be 27 divided by 3 multiplied by 3. So this number will be 27 divided by 9. So this number will be 3. So if you leave it as minus 1, you can see that we get the same result. Okay. So that's just a very nice way of creating NumPy arrays of different shapes that you need. Another last function that I'll talk about is the linspace function. So here what we do is we take a range. So we go from 3 to 27. But now instead of taking a step, what we provide is the number of elements that we want in the array, and you automatically get equally spaced out numbers. So if you wanted 9 numbers, so we could go from 3, 6, 9, 12 all the way up to 27. But if we wanted, let's say 18 numbers, then we would get back 18 numbers here. All right. So that's that. I'll just make one final commit here. And let's just do a quick recap of all the topics that we just covered. So for the first thing that we saw was how to go from Python lists to NumPy arrays, and why we should do that, why we should consider it. We also looked at how to operate on NumPy arrays. So we looked at the np.dot function or the matrix multiplication. Then we looked at the benefits of using NumPy arrays over lists. And then we saw how we can go beyond just one dimension using multi-dimensional NumPy arrays. And then we also looked at examples of working with CSV data files, how to load them, how to perform computations, and then write results back to a file. And then we looked at some arithmetic operations and broadcasting. And then we looked at array indexing and slicing. And finally, we looked at some other ways of creating NumPy arrays, right? So NumPy is, in some sense, it's a very small library because the core concepts that it offers are fairly small in number. But on the other hand, it is a very vast library as well. And it offers hundreds of functions. So if I go back to the NumPy documentation, so on the documentation, you will find a list of all the different functions. Let me see here. Yeah. So there is this section called routines within the NumPy documentation. Let me just zoom it in for you. Yeah. So there is this section called routines, and it is linked to in the notebook as well. So you can see here, these are all the different array creation routines, and then you have array manipulation routines, then you have binary operators, string operators. So NumPy arrays can have strings as well, not just numbers, although we use it mainly for numbers. Then you have some date time related things. You have a bunch of mathematical functions. You have a bunch of things like calculus related functions, Fourier transforms. You have different ways of doing input and output. So it's not just text files. You have a linear algebra. You have logic, you have array operations, here more mathematical functions, trigonometry, and so on, matrices, polynomials, randomization. So there's a whole random section for random sampling, sorting, searching, statistics. So there are a lot of things here, right? And this brings us to the assignment. So because it's not really possible for one person to go through the entire documentation, and I highly recommend not going through the entire documentation and trying to memorize it. That's just not a useful thing to do. But what you could do is just read a few of these and just try to experiment with them and come up with some interesting examples that you found unique, right? That's something that you did not come across in the documentation, something that you came across while you were experimenting. And that is what we are going to do in the assignment. So if I come back to the course page, so that is 0topandas.com. Now here on the course page, you can see that assignment 2 is now live. And the objective of this assignment is to build a solid understanding of some NumPy array operations. So what you need to do is you need to pick 5 interesting NumPy array functions. So you will do that by going through the documentation. So specifically by going through this page on routines. And then you will run and modify a starter notebook. So let me just open up the starter notebook here. And let me just quickly click run here. So the starter notebook contains some instructions. So you can see assignment 2, it contains a bunch of instructions here. But the idea here is that you will go through the documentation and you will pick 5 interesting functions. For example, just as an example, let me pick something related to Fourier transforms. If calculus, this might be of interest to you. So you pick 5 functions. And then what you need to do is for each function, you need to come up with 3 examples. So 3 examples, 2 examples that work and 1 example that breaks. And then you also need to explain the function in your own words, right? And the way you need to do that is by modifying this Jupyter notebook. So you have a Jupyter notebook here. When you run it and open it up, what you should do is give it a nice title. So let's say I'm going to call it something like find NumPy functions you didn't know you needed. Okay. So basically I'm going to pick some rare functions, let's say, and then you can have a subtitle or not, it's up to you, but you should write a short introduction about NumPy. So think of it like a report or a blog post that you're writing. Good documentation is an essential part of data science. It's a lot more important than you might think. So just write a short introduction to NumPy. What is NumPy used for? Use your own words. What do you take away from it? And then list the functions that you will be talking about. You can mention what functions you will talk about, the 5 functions that you have picked, and then save the notebook. So I'm not going to commit here, but keep committing your notebook from time to time. Then here, once again, you need to list the functions, this time inside a code cell. Okay. So I'm just going to show you one example. So I've put in np.concatenate here, but you should change this. So use something else here, whatever you come up with. So list the 5 functions. So like np.concatenate, np.max, np.min, let's say, np.mean, np.median. All right. So these are the functions, statistics related functions I'm going to do. So you just list them here. Then for each function, you need to edit the information. So function 1, np.concatenate. So change this to your first function. Then add some explanation about the function in your own words, right? So you may want to experiment with it a little bit. So you can add a few cells here, do some experiments, and then once you're done with experimentation, you can delete those cells. But finally, you need to have some basic explanation about the function, and then you need to give 3 examples. So here is example number 1, where I'm concatenating 2 arrays along the axis 1. Then you can give some explanation about the example if required, like how the example works. Then we have example 2. So you can try to pick an example that illustrates something different, like maybe instead of axis 0, axis 1, instead of axis 1, I will use axis 0, and I will use different shapes of the inputs. So between 2 examples, you should generally be able to demonstrate the pretty good range of what a function can do. And then finally, the 3rd example should be something that breaks. So this should lead to an error. So for example, here I'm trying to concatenate 2 arrays that cannot be concatenated, and this leads to an error. And then you can provide some explanation about why it breaks. Okay. So the idea here is that you read the documentation, you try to break the function, and when it breaks, you understand why it is breaking and explain that. And when you do that, your own understanding of that function improves dramatically. And finally, you can add some closing comments about when you might want to use this function, where it can be useful. And all of this is just for you to really think about an answer. And then at the end of it, you just commit. So you run jovian.commit. And when you run jovian.commit, what this will do is this will save the notebook to your Jovian profile. Let me just do import Jovian and jovian.commit, and I will set project equals assignment 2 live, and let me grab my API key. Okay, so now keep committing after every function, otherwise you may lose your work. And we've noticed that a lot of you have complained about this, about assignment 1. So now it is committed to your Jovian profile. So now you need to take this link, and remember, take this link and not the binder link, because the binder instance will get shut down. So you take this link and then you come back to the assignment page and you can make a submission here. Okay, so now you can put in the notebook link, and this has to be a Jovian notebook link, and click submit. And that is going to then put it into evaluation. And then we will do the evaluation. Basically what we're looking for is you should have 5 functions, and you should have some explanation and 3 examples for each function, 2 that work and 1 that breaks. And that is the whole idea here. But after doing that, after you're done with the submission, there is an optional but important part that you should also do. So the assignment discussion thread, and you can see here, this is a discussion thread. You will see a continue discussion button. So just like the lecture, we have a discussion thread for the assignment, and this time you can take the 5 functions that you have created and you can share it on this thread. So I can take this, I just created this assignment to live, and I can click the reply button here. So there is a reply button at the bottom, and paste my link here and just mention that, hey, these are the 5 functions I wrote about. All right. So just share the 5 functions that you wrote about. Maybe you can list them out here. If not, you can just say roughly that, hey, I wrote about trigonometric functions, or I wrote about statistic functions, and share the link to your notebook. And this way, what you will get to do is you will get to share your work with the entire course community. You can even share your notebooks online on Twitter or LinkedIn or wherever, and that would require you to make your explanations nicer. One thing that you can do is, before your final commit, you can actually remove this explanation block. So you can take this explanation block and then just get rid of it, so that it looks a little bit nicer, and that will make it easier for you to share it online. So share this on the thread, and try to go through the notebooks shared by at least four or five other participants, so that you've gotten a deep understanding of about 5 functions, and then you learn about another 25 or 30 functions by reading the notebooks of other course participants. All right. And this is going to be really interesting. I am really looking forward to what you come up with, what interesting examples you come up with. Yeah, please do share it. Although that is not a requirement for grading, you simply need to make a submission on the submission page. You don't need to go on the forum, but we highly recommend that. All right. So that is the assignment. And by the way, if you do share it on Twitter or LinkedIn or other places, and if you tag us, so we are at JovianML on Twitter, we will be retweeting and resharing 4 or 5 interesting notebooks every day. So you can get a chance to get featured on our Twitter or LinkedIn as well. So that is the assignment. That's what you need to do. That is the compulsory exercise for the week for the certification. Apart from the assignment, there is also an optional exercise. Let me just find my notebook. Okay, going back to the lecture. So on the lecture page, you will find, so coming back to lesson 3, you will find an optional exercise here as well, 100 NumPy exercises. So this is a bunch of, this is from a GitHub repository. It's a popular repository which contains, this is basically just 100 questions related to NumPy. So you can import the NumPy package, print some version, create a null vector, get some documentation, create a null vector, fill in a certain value. So there are a lot of different exercises, and this will help you get your hands dirty, and this will require some exploration. So sometimes you may have to even search what some of these terms mean, and sometimes you may have to look up the documentation and try a few ideas. And these are 100 problems. So this is an optional exercise, but once again, if you want to really master Python and master NumPy, we highly recommend doing these 100, or at least try and do maybe 20 or 30 of these. Pick a random set of 20 and try and do these exercises. They're also marked by difficulty, so that's up to you. And what you can do is, if you want to get help, I have created a forum category, forum thread specifically for this, for the 100 NumPy exercises. And this is something that you can keep doing over the next few weeks or even beyond. So this is just, it's not a part of the course as such. It's just something that you can keep doing forever, over time. And so please post if you're facing issues, if you need help, or if you need hints, you can post here. You can share, discuss your approach for a problem. You can share your code. So it's okay with sharing the code this time. So you can share your code, and you can work with other community members to figure out the shortest or the most efficient solution. And you can also help others fix their errors and improve their solutions. Please do that. That's a great exercise. I think that will give you enough for at least a week to keep you busy almost on a daily basis. So those are the exercises, the required assignment, and then the optional 100 NumPy exercises. All right. So with that, we complete our discussion of NumPy, and I want to cover another topic here since we have some time. So we've looked at how to use NumPy, and we've also seen briefly how NumPy works with files, but it is also a useful thing to know how to work with files and the operating system, interact with the operating system in general using pure Python. Okay, and that is where we are going to use this other notebook called Working with